Hi, I'm Varsha Mundale from IIPS DAVV and I'm giving a video lecture on greedy techniques. Greedy techniques involve construct a solution to an optimization problem piece by piece through a sequence of choices that are optimization problem defined by an objective function and a set of constraints. Greedy techniques involve the feasibility that is satisfying the constraint locally optimal with respect to some neighborhood or definition, greedy in terms of some measure and irrevocable. For some problem, it yields a globally optimal solution for every instance. For most, does not but can be useful for fast approximation. We are mostly interested in the former case in the class. Here, application of the greedy strategies are, first of all, is optimal solution, which include the change making for normal coin dominations, minimum spanning tree that is MS tree, and the single source shortest path, simple scheduling problem and half-man cost. And the next one is the approximation, which involves the traveling cells problem that is TSP and knapsack problem and other combinatorial optimization problems. Change making problem. The change making problem are given unlimited amount of coins for denominators from d1 is greater than to d2 up to dn. Give change for amount n with least number of coins. Here the question is that what are the objective function and constraint. For this we take an example which includes the d1 equals to 25 coin, d2 equal to 10 coin, d3 equals to 5 coin, d4 equal to 1 coin and up to n which is the 48 coin. Greedy solution involves the values are 1, 2, 0 and 3. Greedy solution is optimal for any amount and normal set of dominations. Here we have to prove the greedy algorithm is optimal for the above dominations. May not be optimal for arbitrary coin domination. So we take an again example which includes d1 equal to 25 coin, d2 equal to 10 coin, d3 will be 1 coin and up to n which is a 30 coin. It includes the minimum spanning tree, the spanning tree of a connected graph G, a connected acyclic subgraph of G that include all of G's vertices. Minimum spanning tree of weighted connected graph G, a spanning tree of G of the minimum total weight. Here we take the example. Now, Prism MST algorithm, which start with the tree T1 consisting of 1 or any vertex and grow tree 1 vertex at a time to produce MS tree through a series of expanding subtree T1, T2 and up to Tn. On each iteration, construct Ti plus 1 from Ti by adding vertex not in Ti that is closest to those already in Ti. This is a greedy step. Next, stop when all vertices are included. Here again is the example in which we start from the A and go to the closest vertex that is B, and from the B we go to the next closest vertex D, and then finally we go to our destination vertex that is C. Now, Prism algorithm involves proof of induction, that is construction actually yield an MST. Main property is given in the next. Needs priority queue for locating closest fringes vertex. The detailed algorithm can be found in Lecture 10. Efficiency of Prim's algorithm involves big O of n square for weight matrix representation of graph and array implementation of priority queue. Next, the big O of m log n for adjacency list representation of graph with n vertices and m edges, and minimum heap implementation of the priority queue. The crucial property behind Prim's algorithm involves that it claims that let the G is the graph of vertices V and E, vertices V and the edges E, be a weighted graph and XY be a partition of V, called a cut. Suppose E belongs to E equals to X and Y is an edge of E across the cut, where small x is in a capital X and small y is in a capital Y, and E has the minimum weighted among all such crossing edges, called a light edge. Then there is the MST containing E. Another greedy algorithm for MST is the Kruskal's algorithm, which states that sort the edges in non-decreasing order of length. Grow tree 1 at a time to produce MST through a series of expanding forests f1 to f2 up to fn-1. On each iteration at the next edge on the shortest list, unless this would create a cycle. If it would, skip the edge. Here the examples are: now, Kruskal algorithm looks easier than Prism, but it is harder to implement. Checking for cycles. Checking for cycles involves a cycle is created if added edge connects vertices in the same connected component. Union find algorithm runs in big O of m log m time with m equals to mod of e. The time is mostly spent on sorting. Minimum spanning tree versus Steiner tree. The Steiner tree involves, in general, a Steiner minimum tree, which is SMT, can be much shorter than a minimum spanning tree, but SMTs are hard to compute. Shortest path include the Dijkstra's algorithm, which says that single sort shortest path problem. Given a weighted connected or directed graph G, find shortest path from source vertex S to each of the other vertices. Dijkstra's algorithm says that similar to Prim's MST algorithm with a different way of computing numerical tables. Among vertices not already in the tree, it finds vertex u with the smallest sum. The sum is dv plus small w of v and u, where v will be is a vertex for which shortest path has been already found on preceding iterations, such as vertices from a tree rooted at S. dv is the length of the shortest path from source S to V of small w of V and U is the length, or we can say that width, of edge from V to U. Here are the example in which three vertices are belong started from the end and the destination vertices is E. Dijkstra's algorithm include the correctness can be proven by induction on the number of vertices. It doesn't work for graph with negative weight. There, Floyd's algorithm does as long as there is no negative cycle. Can we find a counter example for Dijkstra's algorithm applicable to both undirected and directed graph? Efficiency of Dijkstra's algorithm involves big of V square for graph represented by weight matrix and array implementation of priority queue. Big O of E log V for graph represented by adjacency list and minimum heap implementation of priority queue. Don't mix the Dijkstra's algorithm with the Prim's algorithm. For detail of the algorithm are in the text and reference book. So here are we have some invariants in which first invariance, when a vertex is added to the tree, its correct distance is calculated, and the next one is the distance is at least those of the previously added vertices. Thank you.